Hey guys, I hope you all have had a great lunch. Thank you for coming back for the afternoon session. So I just want to introduce our next speaker, Sadman Ahmed Shanto. So Shanto has done a lot of great work with SQuaDDS, which is a tool to generate qubits from Hamiltonians using machine learning techniques. Um, and if you have like qubits that you've measured and you have designs, please contribute to SQuaDDS. But anyways, without any further ado, yeah, give it away, Shanto.
Great, everyone. First, again, thanks to Cody and friends who organized this great workshop. I think it's been a great time. I've learned a lot. I assume y'all learned a lot as well. And the fact that we have everyone in this room together, I think that's really, really great. I wanted to make a couple more shout outs. Thank you to Abhishek and Saikat, who's in the other room, who helped me troubleshoot a bunch of the environment issues that people had. And also thanks to, I'm going to butcher this name. There's someone on GitHub who's like helping fix things on remote people's end. So thank you to the person whose 7 pull requests I accepted, whose name I'm blanking on. Okay, so a quick outline of this workshop. I will talk for hopefully around 20-ish, 25-ish minutes to just covering a very quick introduction to SQuaDDS. Then I'm going to go over what the inverse design and interpolation problem is. Eli kind of motivated this in his kickoff talk. And then we're going to do a crash course into the relevant ML tools that we will be building on top of. And then we're going to start the workshop. So one quick raise of hands if y'all know what these 4 terms mean over here. Okay, great. At least one term. At least one term. Okay. Cans. Okay, cool, awesome. I just needed the background to know what to emphasize on. Thank you all for that. Okay, so what is this SQuaDDS package that you guys have installed? It's actually a 2-party thing where there is a Python package that you guys pip installed, and there's also an associated database that is on Hugging Face. And the database aspect of SQuaDDS contains all the information that you use the API to interface with, and that includes device design, simulation parameters, simulation results, characterization measurements, and fabrication recipes. I will not really talk in too many details about SQuaDDS as a package for today, because that's not the point. But if y'all are interested, I recommend attending my talk tomorrow where I will cover this in more details. But a quick utility of SQuaDDS, or the idea is, as Cody kind of hinted at, is you give it the Hamiltonian parameters, and SQuaDDS will give you the design that you can hopefully faithfully take to the clean room, fabricate it, measure, and hopefully publish. That's the ideal goal with SQuaDDS. So what does the database contain? It has a bunch of device design code and files that are fabrication ready. It has a bunch of device characterization measurements against which we validate our simulations. It has about 5 million eigenmodal and capacitance matrix simulation results that will actually form the training data set for the machine learning games that we'll play today. And it has a couple of fabrication recipes that we use FabuBlocks, which is a great tool. Shout out to FabuBlocks. I would recommend people upgrading the fabrication recipes to FabuBlocks and sharing it with us. And all of it is basically in this Hugging Face URL. It's also accessible via the SQuaDDS API. So with the SQuaDDS API, one of the utilities, again, going from the Hamiltonian to design in this kind of code block. I'm going to skip this because I'll talk about this in details. So QDS, it includes the interpolation logic that we cover in our paper and that I'll describe again in 3 lines of code. It also helps run simulations. Again, this is from ANSYS in the way that we have described in our papers about how to run simulations accurately to make sure that your results are actually giving you the electrostatic distributions that you can then do your quantum analysis on that matches your measured results. So that's all basically taken care of in this one liner. But I will actually, stop here. And in the thing Jens was showing that people usually respond best to GUI. So we'll kind of show you a GUI that kind of eliminates all these things and straight up shows the utility of SQuaDDS. So let me share my screen. So with, let's see, Yeah, so if there's like a command streamlit run, then squads /UI.py, this thing would pop up, and without using any Python, you can just simply use the GUI to get your results. So what's going on over here, you kind of define what system you want to study. So in this case, let's say I want a qubit cavity system. You select your qubit type. In this case, we're only limited to transmon cross, because that's what we have in the database at the moment. You select the cavity type. Route meander is the name for the Qiskit metal component for the cavities. And you select the coupling type, which in this case, the database contains capacitive couplings only. And you select your resonator type. You input the parameters that you want, and you do find designs. And it will find you the designs. So yeah, it finds you the designs. You can just copy these things and use it in your notebook to make your whatever flow you have for your actual designs. And it breaks it down by the qubits, the CPWs, the couplers, and the associated Josephson junction inductance. You can also kind of visually see how far off your target parameters are from what you requested. So that's here as well. And then if you want to just copy paste the Qiskit metal options file, you can do that as well. So all of it is in a hopefully nice enough, intuitive enough interface. So, and this tab has the interpolated results where, as y'all could see, what you wanted is not exactly what was given over here, because this is the closest pre-simulated results that we had in the database. So this interpolated results tab interpolates on top of this closest design geometry to give you a better guess. So that's all here. Clicker. Right, okay, cool. So we're standing on the shoulder of giants. This cartoon represents all of us. What I'm going to say now probably wouldn't make sense, but I want us to stand on our own shoulders collectively. Doesn't really make much sense. But what I really want from us as a community is really contribute to our tools. That's a big call that I wanted to get from y'all before I teach you guys things today. And I've been told if I say the term pull request, all physicists would disappear. So I made a hopefully easy enough contribution portal. Go to this link, sign in with your GitHub account or Google account, and just drag and drop your files. Give me your design files that you're happy with, any simulation workflow that actually gives you results that matches your experiments, fabrication files, anything. I'll take care of the integration. Just drag and drop, and we'll take care of the rest. Just want to quickly look at that. What happened? If you want to be well loved by me, again, contribute to squads. I'll add you to this list. These are all people that I love dearly because they're squad contributors. Okay, now back to science. So this is a slide I stole from Eli. Cool. Yeah, so what's the design problem? The design problem is we have a design, which essentially is all the, your transmon geometries, capacitor pad geometries, your resonator geometries, everything. You can use simulations and analysis tools to go from this design space to Hamiltonian space. It's still hard, as we've kind of the entire theme of the workshop. This is hard, but we know sort of how to do it sort of well. But what I want to talk about is the inverse design problem, where you're given a Hamiltonian, which is this inverse design problem is what we want to solve, really, because all of us have our favorite Hamiltonians that we want to implement on a chip. So this is the problem of relevance to us, which sadly is a very underdefined problem, and it's very difficult to solve. So in SQuADDS, how we have solved this is essentially by having this mapping of, we have a bunch of simulations that take us from this design space to Hamiltonian space, and that's how we can just, like, whenever a user queries for a Hamiltonian, we can just send them back to a design that has been pre-simulated. That's how we kind of solve it. But of course, it doesn't scale super well for arbitrary geometries, right? So going back to that point, what happens in SQuADDS is, again, the user specifies, the cartoon went by real fast. But what happened was the user specifies some parameters that they want in Hamiltonian space with a metric, and SQuADDS essentially uses that metric to find the closest pre-simulated Hamiltonian point and maps it back onto a pre-simulated geometry point. So the interpolation problem is essentially how do you actually get an even better guess to give the user a geometry that did not exist in your data set, but we can kind of faithfully say that it is a better geometry for your own target Hamiltonian. So that's the interpolation problem. So this is the interpolation algorithm we have on our paper. It looks pretty complicated. It is complicated. And in this case, when I say we, I mean Eli, solved this by essentially, the idea is essentially this, like you are scaling various design parameters and compensating for that scaling with other design parameters to kind of iteratively match what the user wanted. And as you can sort of see here by these scalings that I have, it's convolutional in the sense that you're scaling your design parameter using variables from the Hamiltonian space. So it is complicated, and it's not easy to come up with a general algorithm that handles this mapping for various geometries. This was a tough task. I hope Eli agrees. There we go. So, but it does work sort of well. It works pretty well, I would say. Making the counterpoint now. So how we validated that interpolation algorithm is with this following like simulation experiment where the user specified some Hamiltonian parameters that they want. So this one red cross you can think about as a 4-dimensional input, kappa, cavity frequency, coupling strength, and harmonicity. And of course, SQuADDS gives back to the user a geometry that has the corresponding Hamiltonian parameters closest to what the user wanted. But then we also give to the user a interpolated design, right? That has not been pre-simulated. But in this experiment, we actually simulated that interpolation result. And as you can see, it matches the target a lot better. And we have done this for various points in the design space or Hamiltonian space. And some of them are here. And in all cases, except for the one that I've highlighted over here, we get a better agreement to our target with the interpolated result than what we had. And we can totally explain the reason why I included this here is because we intentionally chose these points to be outside the convex bounds of our data set. And we know the interpolation would not work here. And it was a sanity check, yes. For the cavity frequency and kappa? Yeah, like the algorithm is the same. It's just different points of view. Yeah. But point is, it works. But counterpoint is, it is problem specific and design specific and does not scale. So I'm going to start with the workshop stuff. One of our objective is how to use SQuADDS, Qiskit Metal, Palace, SQDMetal, all these things, all these really nice tools. How to use these machine learning systems to solve the interpolation problem that I just talked about. And how to use machine learning systems in a way that we're not just basically, using machine learning for the sake of machine learning. We want to understand the physics that is going on within our data set. So that's one of our objectives for this workshop. Yeah, in particular, what we want to learn with this particular machine learning system is for a given Hamiltonian parameter, what are the design space variables that affect it and how they affect it? These are the 2 questions we want to answer. Any questions so far? Yes.
Looks like you have a single qubit and the ability to
For the examples that I've showed you so far, yes.
And
we have done the most work on this qubit cavity pair. And this is what I'm going to stick to for this workshop. There's some work that we've done, but we haven't really pushed it or publicly.
Yeah. So I'm curious, how did you think about your training data set? And
I'll cover those things in the workshop, the training data set part. Yes. This plot? Yeah. Yeah, these are the same points. This is like a 4-dimensional, I don't know how to represent 4 dimensions with my hands. This is a 4-dimensional point that I have 2D slices. So it is the same thing, but yes, it's because, so I should have included a figure, basically these points are outside. There's like a very nice phase boundary within our data set, which corresponds to we're working with regimes that are transmon. And these parameters are, well, it's like around EJ over EC of like 10. So these things don't work because it's no longer it's like offset chart sensitive, right? So we know this is not going to work. But we want to test that it actually, if it's not going to work or not. Yes.
I just wanted to compare that with I'm looking at the average.
Yeah, great question. I don't recall the exact value off the top of my head, but it's between 3.7 to 4.2, like qubits that we usually operated within the lab. First, okay, I will move on to the next parts. Okay, so a quick. Okay, firstly, I apologize in advance to any theorists or very like math heavy people over here, because I'm gonna throw very math heavy things, but explain it in a very hand wavy way. So I apologize in advance. But if I were to really be very rigorous, it's gonna take more than 2 hours to just cover cans. So I started off with, it was a hard task. So I asked my friend ChatGPT that, hey, I'm gonna give a talk to a room full of quantum physicists who are extremely smart, but may not be aware of the latest advances in machine learning. Could you give me a very simple sentence that I can use to introduce them to Kolmogorov-Arnold theorem in a way that don't offend the theorists and lose the attention of experimentalists? So it gave me a sentence. I don't really like it, so ignore that. Could you hide the chat? But the idea behind the Kolmogorov-Arnold theorem is essentially that it is a universal function approximator where you give it a multivariate continuous function and you can write it in terms of additions of other univariate functions. If again, mathematicians, please don't hate me. I'm sure there's like domains over which you have to define this, but this is a very, very solid thing. This is a cartoon that I screenshotted from the talk given by the paper, the authors of the paper, where again, they're just showing that there's a one-to-one mapping between the universal approximation theorem, which is the backbone of all neural networks, and this Kolmogorov-Arnold representation theorem. And just for context, this paper came out 2024 February. I don't think that's right now. It's like 20,000 citations or something. This is a very big deal in the field of machine learning. And also, I think there was like 3 talks in the last APS of them applying this to physics. So it's only going to get better from here. So could you hide the chats? So on the left, we have a multi-layer perceptron, also known as a neural network. The CAN also has the exact same structure, but as I'll explain, the geometry is a little different compared to your traditional run-of-the-mill neural networks.
It's very easy.
Okay. This is what happens in the lab. I mess up something and he helps me. Thank you, Eli. So for the neural networks that we all love and use, I think, the idea is that the activation functions are fixed. We select whatever activation function we love, ReLU, TANH, whatever, sigmoid, whatever you want. And it's the weights that get changed when you are training the network to map on whatever you want or whatever the inputs to the target. So that's the paradigm for neural networks. For CAN, it's kind of flipped upside down where the weights are fixed. It's the activation functions that change. And I'll hopefully motivate that this structure gives us insights about, like this makes this entire thing not a black box anymore, because you can kind of see how the network is learning. And that's very powerful for physics. So again, what happens when we train a neural network? In this very simple neural network, you have 2 inputs. You have, again, trainable weights, and you have a sigmoid output function or activation function. The neural networks essentially find depending on what your loss metric is, there's some loss landscape. The neural network finds the best weights that correspond to the lowest loss. That's how it is trained. Exactly one-to-one mapping for a CAN, but in this case, rather than these slides are, by the way, from Serrano Academy, who posts like really nice, easy to understand YouTube videos of these advances in machine learning. So I would recommend subscribing to them. But again, the idea with the CAN is you are, rather than changing the weights, you're changing the space of functions. And you find a set of functions that minimize your loss. Natural question is, aren't functions like continuous variables? How it's like a huge, huge space. How are you doing this? Very, very natural and good question. The idea, or at least the idea in the paper, is you replace functions by what is known as B-splines. And what's being shown over here is, let's say, the functions that your system is trying to learn over. It's being represented in this case as constant splines, where you're telling the system that, hey, the splines that I want are constant. They will take a single value, and I want them to have a grid of 3. So over here, a function that, I don't know, is it exponential? Maybe, is going to be represented as these 3 numbers. And for a function that's sinusoidal, would be represented as this. And as you can imagine, by giving it a higher grid spacing or giving it higher order polynomials for the B-splines, you can really approximate any function. But the training time will basically not, I don't know how that scales, but it takes a lot longer if you're increasing the complexity of the B-splines. This is, I promise, the last thing I'll talk about machine learning. Cool, workshop time. Any questions before I get started with the notebooks? And another comment is, I'm going to go over the notebook in real time. Even if you don't have things set up on your system, that's okay. There's going to be parts of the notebook where I have tasks for you all, and I'll tell you when I'm done talking. And once you guys get started, I'll just walk around and help people who have issues. So, yes.
So the difference between instead of exact function, you're varying the activity.
Yeah, in a simplistic way, that's basically what it is. Of the weights are fixed, because the activation functions are changed. So the weights are fixed at 1. That's fixed. Was there a question? Yeah.
So each activation function corresponding to has parameters.
N by m, because splines times the polynomial degree of your B-spline. Sorry, grid spacing times the B-spline order. Not sure. Doesn't matter for this workshop. Good questions, yes. Yes, it is, yeah. Okay. So given that, again, for neural networks, you have, the weights are scalar values, right? You have n density layers, it scales by n, but this is n times L, I guess, because for each grid, you have 2 parameters that you're changing now. So it does train, it takes a longer to train, but the reward is it's explainable. Okay. All right. So I hope everyone has the latest version of the repository pulled. If not, please do so in order to follow along. But if not, again, no worries, because I'm going to go over it anyways. Okay. Cool. And for this tutorial, since this is actually a good point, I was discussing with Abhishek about this, and Jens raised this point. A lot of people have issues with the environments, right? I think it's a us problem in the sense that us as physicists, we're kind of used to just doing everything in one environment, but the standard practice is always to have separate environments to do separate things. So in that, yes.
Along those lines, so there were 2 kind of sets of instructions.
Yes.
Right? The one that's just on the main page of the repository, and then like the advanced
Yes.
track. Did you want us to do separate environments?
Yes. Yes.
Okay.
Because that's the point. Because the design and the SQuADDS and Qiskit stuff is in one environment, the machine learning stuff is in another environment. That's an easy way of not having, installing one package, breaking everything else. And that is the standard practice, which we should, as a good community of people, follow. Okay, let's do this. So I think back to the question that he's asking, we're going to create the data set for our machine learning game. Execute these cells. I already did this. Installing or importing the packages I need from SQuADDS. What's going to go over here is I'm basically defining the system, which in this case is the capacitively coupled transmon cross qubit to the cavity route meander. It's a quarter wave. And then I feed this to the analyzer object from SQuADDS and build this create system df commands essentially computes all the Hamiltonian parameters for the entire data set that we have. So this is done in 15 seconds. Over here, I am giving it some predetermined seed parameters. So these things you folks can imagine as being Hamiltonian parameters that you'd want. Yeah, that's one way. But this is, for this example, I'm going to use this to create my training data set. Because the thing is, the G is computed based on top of again, I'm not going to go into too much details, but for our data set, we don't have a fixed G value computed because G is a function of the required cavity frequency. So you need some sort of seed, a target input Hamiltonian to kind of add this, all the Hamiltonian space parameters. So within SQuADDS, since we want people to do machine learning stuff with SQuADDS, and there's folks in Fermilab and Pacific Northwestern, they're doing a bunch of great stuff. So we use this create qubit cavity training data set, which takes us the analyzer that you specified and a seed data, and it will essentially in this training DF, which someone had a question about the training data set. This is what it's going to look like. So it has 13 columns. So columns include, let's actually look at what the columns are. And there is like what 133,000-ish data points. So this data set has claw length, which is a design parameter, cavity frequency, Hamiltonian parameter, kappa, all these things. Basically, it's a combination of the design parameters and Hamiltonian parameters that we have in a nice ingestible format for machine learning training. So the first thing that people do in machine learning is you don't just give it your physical data set. There's some pre-processing that you have to do. This is known as feature engineering. So we're going to do that. At each point in this notebook, when you see this load ext auto reload, this is where me signaling that you have to change your environment to the machine learning stuff. So I just did that. These are all tools that are very near and dear to ML people, importing all these things. Then creating some subdirectories where I want to save my data and models. Again, reading back the training data set. SQuADDS shouldn't have any duplicate entries to begin with, but just to be safe, I'm just doing a drop duplicates and resetting the index. And now over here, I am kind of specifying the Hamiltonian parameters and design parameters that I care about for this workshop. And extracting them in an XY sequence, meaning that X is the Hamiltonian parameters and Y is what I want the design parameters corresponding to those things, because we want to solve the inverse design problem. I'm going to run these cells. And then for any machine learning system, you want to take your entire data set and split them into testing and training that's needed for the machine to robustly train. Doing that, this test size 15% is meaning that whatever 133,000 rows times 0.15 is used for validation checking, and the rest is used for training. And then over here, as my processing or as a part of my feature engineering, what I'm doing is I am giving it more training columns by using this polynomial features. The idea or what's going on over here is the data set, for example, contains what in terms of the design space: cross length, claw length, coupling length, total length, ground spacing, right? A polynomial transformation on this of degree 3 means that it will basically multiply each element as a cubic polynomial. So it's going to include terms like cross length squared, cross length cubed, cross length times total length times claw length, all these things, because there might be some Hamiltonian features that map better to polynomial features of these individual design columns. Did that make sense? So it's also standard practice in machine learning. And to demonstrate this is what's going on. Our training data set had only 5 design columns, whereas, our training data set before I did this had 5 data columns for the design space. And then the one that I'm actually going to be training on has 55. because I have done this cubic polynomial feature scaling. The last thing that we do is, again, machines are, you have to convert your targets and your training data all into basically normalized values. So scaling it down, getting rid of all the physical parameters, the units essentially. And now this is a very, very simple MLP, a multi-layer perceptron. I have randomly this code was written back in 2022, so it's pre-ChatGPT era in a certain sense. But I'm sure you can ask ChatGPT and it can give you something better. But for the sake of this workshop, I'm sticking with this. It's a 3-layered system, if I'm not wrong. Yeah, first layer has 256 neurons, second has 128, third has 64. And these are like normal. I don't fully understand these requirements, but this is just standard practice in the machine learning field. Included them, and this basically creates our neural network. And now I will train this network, and I'm telling it that, okay, if there is no improvement in the training for 20 iterations, stop. I don't want to waste my resources. But I'm going to stop it at 500. If it doesn't finish, then I'll move on because we're limited by time here. So I'm going to start this, and while this trains, it probably takes like 2 minutes, 3 minutes. Any questions I'll address. Mm-hmm. Great question. So these are parameters that the data set that I'm referring to here are the parameters that I swept over when I built SQuADDS. So for example, tell me the 3 parameters you just said. Yeah, I could have included a gap here as well, but I chose not to. But there's like certain parameters I didn't change. So I just kept that fixed. Yes.
So once you have transform with more kind of a different geometry in terms of the paths, it's not an Xmon or maybe just, if you have the ability to handle more varied designs.
Yes, we have the ability, but as Eli said, we need the data first. So if you give us the data, we will handle the stuff and we will add it.
Do you have is just that right now, is it just on Xmon or do you have Xmon maybe in parallel?
We have Xmons, we have some like custom components that we use within our lab, such as dissipators, but we're kind of limited because again, we want more data. Please give us data. Yes. Yeah, sorry.
On your point of data, I was wondering, and this is what I was trying to ask, have you thought of generating random design and getting everything from it, and then training and maybe selecting the one that is good?
Yes.
While you are trying to go to the target.
Yes, we have a lot of things we've thought about and want to do. I think we're waiting on getting money to do these things. So
we also have a fairly maybe a 30% variation on that. So begging for design, we're not going to add database.
Right. Other questions? Sorry.
All data that is creating
With hard work, time. Yeah, that's honestly, like, you guys are laughing, but that's true. We built this ourselves. That's like, read the paper, but that's not what I meant to say. We have these experimental devices that we've characterized in our lab, and then we have fine-tuned simulation methodology until we could get it to reliably match these measured results. And once we have mapped it on, then as Eli said, we were changing each parameter within 30% and sweeping and building the database because we are reliable that. Yes. Yes.
then you vary within 30%.
Yeah, of the design parameters.
What 30% is design?
For example, if your cross length is like X, we're going from 0.7X to 1.3X. That's arbitrary, so choosing. Yes. I will come to your question. Let me start one other training and then we can talk. Okay. So let's look at how this training finished in 3 minutes. This is a number I want you all to remember for reasons that will be clear soon. Let's see how the training looked. Yeah, the model did learn something. There was not clear overfitting. The losses are not horrible, not great. Let's move on. It is, again, a very simple model as I've kind of started. So right now what's going on over here is I'm evaluating the model, the trained model based on the testing data set. And one thing that we should do is, again, remember, we had everything in just arbitrary scalar units from normalized units, and we're inversing the map. And let's look at what the model came up with looks like, the results. So yeah, so ideally, if everything was like the variance is pretty high in the ground spacing, and the reason is in the simulations that we used to build up our data set, we only chose 4 ground spacing parameters for each design. So there was not a lot of training data set to begin with for it to learn how it's mapping on. But for other variables, seems like cross-link, claw length did a goodish job. Coupling length, yeah, not horrible. Total length, not horrible. Again, it only trained in 3 minutes, so it's not a sophisticated model. And the fact that it could give us something that is, not wonky fully, it's a good sign. And we'll validate it in just a moment. Yes.
Like so the file length, for example, isn't that a parameter? So what does it mean, actual versus?
Yeah. So yeah, sorry, I went over it real fast. So basically, the actual parameters are for the test data set I did. I know the real values of remember I gave it the 5 Hamiltonian numbers, or I created a seed data file. I know what the Hamiltonian parameters are for each of these claw lengths. Okay. I trained a model that only uses Hamiltonian parameters to predict their corresponding design parameters. Right. So if this was just single points with the gradient of 1, that means the model learned the EM simulation and the quantum analysis fully. The variance and the fact that it's linear means that it did learn something, but the variance means that it's not fully robust. Did that make sense?
Predicted, like given a set of input Hamiltonian parameters, like in the after the training test, it kind of put in like a G and a kappa and then spit out a column.
Yeah, and it maps onto what the actual one was for that thing. Yes, I will get back to questions. I'm sort of worried a little bit about time, so I'm gonna, because there's a lot more interesting things that I want to cover. Cool. Yes, and I'm still a little stressed. Okay, cool. Yes, just for validation. So what am I doing here? So also I wanted to look at, for all these data points, I wanted to kind of look at how the predictions from the machine learning model compare against the closest value for those predictions within the SQuADDS database and the interpolated numbers that our algorithm gives us. And this is what it looks like. Again, the blue curve, the closest means that this is coming from the database. It's pre-simulated. The green curve is the perturbed or the better guess variable for those input Hamiltonian parameters. And the ML, or the red pink curve, is what the machine learning model that we just trained predicted what the design parameters would look like. So again, it learned how, at least again, from a bird's eye point of view, the cross-link, claw length, coupling length, it seems to have picked up the trends more or less correctly. Ground spacing, not so much. We know why. Total length, yeah. It actually, no, total length is kind of nice because it matches our interpolation algorithm, which is good. So it did pick up on the trends sort of well. So now we're going to go to the second part of, again, I promise I'll get back to the questions. I'm just going to start the simulation. So what we want to do right now is we want to take one of the predictions and run a simulation on Palace and see where it lands actually. So that's what we're going to do now. Okay, I'm going to change my environment, running these things. These are all methods essentially. Just I saved our model, saved the predictions, reading it back. I'll take a question, sorry. Eli had a question. Other Eli, sorry. Okay.
that makes sense.
Your question?
Question or comment. So, especially about your training, so you data set and you're relying on the parameters measured in the lab and then reported in literature.
Put in what?
Reported in literature.
Yes. Mhm. Mhm.
But we also know that the same design in different labs corresponding to different labs actually can give you different G values.
Right.
Someone's calculating where it's 4 to 7 instead of 5 to 6. So maybe like everything we talked about it, you are
Yeah, great question. And the training in this case is just the model, right? I think there's a distinction. I want to make the distinction between training and the training data set, two different things. The training data set in this case I just created in front of you all. So it's giving it a seed. But the point that you raise is actually very important, right? Because true, the simulation methodology that we've validated is on devices we made in our lab. But actually within our lab, we have two foundries. One is our postdoc who makes the devices in our lab, and one is MIT's Lincoln lab. And we've actually used the same methodologies with the same practices, and we've found the hyperparameters of our simulation technique and the way that we do it actually accurately mapping the electrostatic simulations to our Hamiltonian results. So it has been validated, if that made any sense. But it's the same, like we're not changing, like one case you're like, yeah, we're using aluminum on silicon, and the other case using aluminum on sapphire. No, we want to keep the only thing we wanted to change was the foundry. Eli had something to add.
Following up on that.
Yeah.
Take a measured device. We make sure that our simulations will match it to within the tolerances that I talked about in the last talk, which is within a couple percent or most parameters. And we make sure that the same simulation methodology matches a broad range. Then we vary the device design parameters, like the geometry, simulate those, but it's only the simulated stuff that actually goes to the calculation. So everything that's being trained is only on the simulation, not on the measurement. To sort of keep it consistent. Sorry, I understand that. That's a very point. But even for simulation, when we do simulation, this is fine. The perfect metal is fine. And the substrate thickness and the substrate size. Yeah, that is as accurate to the real device as we can make it to within the limits of what we are allowed to do. So there are things that we're not allowed to disclose, in which we deliberately obfuscate them and prolong in a way that.
And we actually do have in our review paper, we do have a plot that when we don't obfuscate those parameters, we actually hit them exactly where we expect them to be. I will get back to the question. So again, right now so this is the variable where there's like, 3 different OSs I can see over here. Wherever you have your palace installed, change this variable to that, and then you can kind of move on with the rest. So the idea is I am essentially taking the predictions from the machine learning model, and I'm just going to simulate a single geometry, which will contain a qubit capacitive coupled to the cavity. And yeah, let's see. Let's build it in Qiskit Metal. I'm using SQD Metal. Shout out to them. They're a lab in Australia. They have done a lot of great work in doing this tight integration between Qiskit Metal and Pallas. They're incredible people. I hope they're here in the Zoom call, but I wish they were here in person as well. So over here, all these methods are, again, I assume most people have worked with Qiskit Metal. It's pretty straightforward, just grabbing the geometry parameters from our trained model and instantiating all the right Q components. And the final design would, but it was there, my screen changed. So that's the geometry that we want to simulate in Pallas. Okay, these 2 parameters I recommend instantiating whenever you use Pallas to make sure things run smoothly. Over here, there are certain parameters I kind of want to talk about. So how many people have used Pallas before for running simulations? Great, cool. How many people have used ANSYS before for running simulations? Okay, so in ANSYS, what's the flow? The flow is you make your design basically like how we did, right? And then you call like ANSYS QRender or whatever. It gets rendered to ANSYS, and then you use the nice methods as .co-developed to run your eigenmodal simulation and do the EPR analysis or LOM analysis, whatever you want. The flow with Pallas is different in the sense that before this SQDmetal integration, what you needed to do was you had to manually generate a mesh file corresponding to your design. Then you had to also manually assign ports needed for your eigenmodal simulation. You have to manually assign the inductive elements. And so yeah, that's one thing. One input is the mesh file. It's a .msh file. I think it handles like 7 different types of files, right, Abhishek? And the other thing you have to feed into Pallas is a JSON file, which is essentially the analogous part of this JSON file to ANSYS is your setup that you give to ANSYS whenever you run a simulation about saying that, oh, my eigenmodal simulation, I want to start at 3 gigahertz. I want to, the tolerance that I want, how many converged passes, all these hyperparameters. So in that JSON file, you define that. And you also define the physics of your design in the sense that the Qiskit metal to ANSYS pipeline automates these things. It assigns the metal layers as perfect conductors. It assigns the substrates correctly. It assigns the loss tangents and everything. You define it manually without this SQDmetal integration in that JSON file in Pallas. They have really good documentation that's easy to follow along. But what the nice thing about SQDmetal is it handles a lot of this automation for you. So some of the parameters that I've listed over here that I want to go over is this. So this mesh refinement, if you look at the Pallas docs, it takes integer values. Each value over here represents a mesh algorithm that they use behind the scene for how they evolve how they adapt their mesh after each convergence. One thing we found, really the reason ANSYS makes money is because their meshing algorithm is great. You can give it like a really poor seed mesh and it will just do a great job. And they don't publish on it how they do it, but that's their secret sauce. Pallas has done a great job in just open sourcing everything. And I think a higher value for this mesh refinement means whatever the corresponding mesh algorithm that they want. So that's one thing. You define whatever your dielectric material is. Again, SQDmetal, essentially you give it silicon. Behind the scene, it will map on, create your substrate, give it the right parameters for silicon. One nice thing about Pallas is you can also define the crystalline axis of the silicon. So that's pretty cool. Same thing, starting frequency, exactly what it sounds like. How many frequencies you want to save in this case, I said 3. How many solutions you want to save. This is for visualization, which I'll show in a moment what that means. Solver order, again, a parameter from Pallas. Higher order means higher accuracy. Choosing one because I wanted to finish on time today. Solver tolerance, analogous to the tolerance for ANSYS. Max iteration, I'm just saying for each. This is not the same as ANSYS's max iteration. It's just for each adaptive mesh refinement, it will just do it 3 times. That's what this means. Higher iterations, of course, will give you a better result. These are the mesh cell min and max. How many points you want along each mesh cell, fillet resolution, and then you can scale this parameter to how many CPUs you want. So this is defined as user-defined options, and this goes straight up into that JSON file that you can also manually define. And then you pass this JSON file to this Pallas eigenmodal simulation object. Over here, I think someone asked a question about HPC in Eli's talk. But it's very easy by essentially changing this parameter to HPC and on the back end, connecting it to your node and whatever your Slurm job is, and it just runs fine. So it's super nice. Run the cell. Over here, what I'm doing is, again, just giving it, since Pallas is not as great as ANSYS in doing this adaptive mesh refinement, I'm just kind of defining it on my own. So this add metallic layer, I'm just saying that for everything that's in the substrate, I don't really care that I don't need too great of a mesh. I do want a ground plane with certain mesh. I gave that. Fine mesh in rectangles. So these, when I wrote this tutorial, I realized it looks like magic numbers, but these are not. I get what the bounding box is for my transmon, and I took these numbers and just gave it a bigger number so that I just have a higher mesh in the transmon neighborhood. I'm creating ports on my launchpad, so there's going to be ports on the transmission line with these numbers. I'm creating, so I'm giving it my junction that I defined with the correct inductance value. I chose a random, not random, it's 10 femtofarads as the capacitance of the junction. You can choose if you know what this number is. And then I'm just saying that, okay, the other way, like SQDML has done a great job by adaptively also like easily targeting each Q component. So for example, you can just say, hey, I want my feed line to have this particular mesh, and it does so. So I included that. And then for EPR, which Pallas already, if you have any inductive elements in your Pallas simulation, it will just compute the participation ratios for you. So I'm giving it the interfaces for my simulation. So I'm using silicon, aluminum, vacuum. Okay, then all you need to do is prepare a simulation. It's creating the mesh file, it's creating the JSON file. It doesn't take too long. Cool. And then once this is done, we would want to look at the mesh file to see if our object's rendered correctly or not. So running this. Let me share the right part now. So this is what the mesh looks like. Pretty nice. Okay, closing this. Okay, happy with that. Oh, this is a part. So everyone with the Windows system, ignore this. Do not run the cell. Everyone with the Mac or Linux system that has a Pallas build that is from 2025, run the cell. I just had to include it because I wanted everyone for this to work with everyone. But now I'm just going to run the eigenmodal simulation and address questions. Yes. Nope. Yeah, it's not essential. There's some, I forget what the environment variables are. It's like Qt metal, set it to 0. Huh? Yeah. Just make sure it rebuilds, like make sure the components will get actually rendered. Yes. Yeah, you don't need that. Yeah, we have some ideas on fixing that we'll talk about Thursdays when the meeting is. Yeah, questions?
Said, I realize this isn't an SQD metal workshop, but have you had a chance to play with their console integration?
Sorry, continue.
From what I understand, the Python API for console is a little bit to be desired. How stable is that?
Great question. I haven't personally played with console, but I really like the folks at SQD Metal. I think they've done a decent job, but this is all me guessing.
So the person from SQD Metal worked on this, told me that they initially started the project for console, with license and whatnot. And stuff is like that helps.
Yeah, there were questions that I didn't address.
Talking about splitting the data set, that's splitting it with testing or also validation.
Yeah, great question. So the testing and validation are interchangeable. So the training set is what it uses to train. And the testing set is once it thinks like, oh, I've trained enough, let me see if I could predict this data that I haven't seen before, which is from the test set. So that's used for validation. Yeah. I remember there was questions here, I think. All right, but okay, cool. So this is, I'm not almost done. So we have run eigenmodal simulations. I can assume like 80% of us. How long do they take usually? It's not a trick question. Hours, yeah. So this is done in 2 minutes, 33 seconds. But can we trust this? Is the second question. So let's look at that. So these are the 3 modes that it gave us. One it found at 3.9 gigahertz, 8.4 gigahertz, 9 gigahertz. Ignore the kappa values for now because it has 5,000 kilohertz kappa. So let's close our eyes to that. But let's see what we expected. We were expecting the geometry, which came from the machine learning model for 4.6 gigahertz for the qubit, 6.9 gigahertz for the cavity. So maybe the first two modes are the qubit and the cavity modes. Let's verify. Again, the simulations are not correct because I intentionally gave it a really bad tolerance, and it's only running for 3 consecutive. The fact that it gave us numbers in the same ballpark, I find that pretty impressive, but you all can disagree. That's totally okay. Okay, so I'm going to open. So using ParaView, I'm gonna open the files for visualization. Yeah, as you can, did not change. Where did my Zoom go? Oh no. Okay, so I just opened ParaView to see the mode distributions. Have any of y'all used ParaView before? It's not necessarily a tool for the quantum community. It's just a very powerful tool for visualizing a bunch of EM. It's a very common tool within the semiconductor people, I guess. Yeah, multiphysics stuff. Yeah. So let me make it. We want to look at the magnitude of the energy distribution. Surface doesn't make sense. Let's look at the wireframe. So our mode. This is indexing from 2 is our mode 1. Let's see. We thought it was going to be the qubit mode. Is it really the case? Wait, sorry. 1, sorry, my bad. 1 was the qubit mode. It is. Can you see? Yeah. It is a qubit mode, so that's good. 2 should be the cavity mode. Kind of difficult to see on the screen. Yeah, I guess you can sort of see it. Is it visible? Yeah, sorry, the projector, but the 2 is the cavity mode. Sort of see it, I don't know. Yeah. You over here? For the interest of time, you can look at my computer. It is there. I'll take a screenshot, post it there. Let's move on, because there's a lot more interesting things I want to talk about. Not that this is not interesting. Let's see. Cool. So yes, the mode 1 is the qubit mode, and mode 2 is the cavity mode. Let's see. So as a very good grad student, I'm going to do something that my advisor very explicitly said not to do, and do some EPR analysis on this result. Yes.
Maybe I missed it. Is it an adaptive meshing algorithm?
It is, but within this adaptive mesh, there's like different algorithms that they use for like different like domain. I'm not an expert in that domain decomposition stuff, but those numbers get mapped onto a different one. And I think Hugh Carr is the guy who develops these things. He recommends a certain. I think they have a document on Palace, right, Abhishek, where they talk about how AWS does their qubit simulations.
Yeah, they do have.
But they also have like a JSON file. Yeah, I'll post a link of what AWS does for their own qubit cavity simulations with Palace. So there's a reference material for that.
A few times further.
Yes, I have. Yes, great question. I have done that when I've increased. I just wanted it to run in time so that I could continue talking. But it does. The results get better when I let it run for longer, as you would expect.
Okay.
But I haven't done a hyperparameter study because we need to get money first for me to spend time on this.
But it's not way slower. Yeah. And for us, hyperparameter compute is too much free.
Yeah.
Whereas The difference between 2 hours for a daily simulation and 4 hours for
Okay, so just something. Sec, let me get the right file. This is giving it the right correct path to the file. My bad, 1 sec. Sorry, I did not give it the right file. Almost there. For TPR. Okay, yeah, let's compute the, what the heck? My bad. Finally, okay, 1, 2. Okay, so we get the participation ratios for the 2 modes. And again, I'm just gonna, the reason I'm doing this EPR analysis is to kind of harp on the point that Eli raised. So I'm gonna recalculate these things and compare the numbers. So what I've done over here is computed EJ, all these parameters from the EPR results, and also included stuff we got from SQuADDS and some of the equations that when you don't take the rotating wave approximation, we've included that as well for comparison. So EJ from the EPR results 16.3, from SQuADDS is 27. EC is sort of the same, I guess, from both. EJ over EC, one says 45, one says 83. LJ was something we fixed, so that's that. The capacitance from both are the same, which makes sense why EC is sort of similar. Participation ratio is just from the simulation. This is also from the simulation, the qubit. That doesn't sound right. I think I parsed it a little differently. But the point that I wanted to kind of, parsed a value differently. It was EPR analysis. I'm going to ignore this for the time's sake anyways. But the results when I did it correctly was this. Ignoring the kappa, which is, this was a bad simulation because I intentionally chose it to be. The other values have inaccuracies that we still don't tolerate, but the fact that we could run it in reasonable time on a free software is promising. And I would hopefully I'm going to make a claim that by this time next year, our community moves towards Palace completely and forget census. And these results hopefully are within the bounds that Eli set. So I think we should make it a goal for next year. So, yeah, I kind of already talked about it. So either this result is saying that either our model was kind of incorrect or the simulation is incorrect. In this case, it's a simulation. So that is that. Your first task that I was going to give is essentially to do this hyperparameter study of the simulations. Change the iterations, change the meshing, see how it looks. So that's one thing that I want you all to do. But we'll talk about something else, and then I'll let you guys actually do it. Questions before I move on to the next part? Oh, actually, let's take a break. Sorry. Let's take a break. 5 minutes break. Yeah, so what I'm going to do, we want to essentially use this CAN network to find out how the cavity frequency depends on the total length, its total meandering length, and its coupling claw length. So we want to find out this dependence. So we set our target feature to the cavity frequency label. We extract the input features from this dependency summary variable. And over here, it's a similar. So for CAN, you need to structure your data set in a way where it's the same idea, where you're giving it the test train versions for both the targets and the inputs. But it has to be in a torch tensor format because we're going to use PyTorch underneath the hood. So this is what that's doing. So just so that people can understand what these things look like, let's look at some of the variables. So X train is essentially the first part corresponds to total lengths. Is that correct? Yeah. Total lengths, and the second part corresponds to the claw length. So these are in microns. And so this is all arranged in a tensor format. So now, so this is something that, an advice, if any of y'all want to do ML stuff and you want reproducible result, you need to set a seed that's fixed. Because if you don't do that, you run your notebook, your numbers are not going to be the same. The model will get to the same formula, but the actual numbers have some fluctuation because these are all stochastic systems by default. So and I struggle. I thought I did something wrong. I spent an embarrassing amount of time trying to fix this, but it was just I did not set the feed or set the seed. Fixing that, importing the CAN. So and then setting up a CAN model, which essentially, and I'll explain what this diagram means in just a second. Setting up this CAN model in a 2-2-2-1 structure, which represents this network. So these, should do it on the screen. These two nodes are the input parameters. The first one is the total length of the cavity. The second one is the claw length. These two blocks are the activation functions that can, just using the data set that I gave it, found out that, hey, what should these functions look like? I didn't give it any information. And then it just adds it. This is what this thing is saying. And then it essentially is the combination result. It then flips it. So it's like a negative sign because, of course, and this top part is the cavity frequency. So already you can see that, okay, for linear increases in total length, this is kind of like doing a -1. So there's some interpretability of what's going on. So that's what the structure looks like. We want to then actually train the set. We just created the neural net. We train it with similar, like you give it some sort of iterations that it's going to train over. But there's these two parameters known as lam and lam entropy. And I kind of described them over here. It is a little complicated, but for our example case, what these numbers mean is as follows, where for lam, a higher value forces the network to use fewer basis functions and promotes sparsity. Okay, what does that mean? So remember, for CANs, you're not changing weights anymore. You're changing activation functions, right? So if you give a higher lam value, it will limit the number, like the set of basis functions. So for example, underneath the hood, it's using a basis function of polynomial. If you, let's say, give 1, then it will go up to like degree 30, let's say. If you give it a smaller value, it will go up to like degree 5. So that's just limiting how many basis functions it's supposed to train on. The lam entropy, on the other hand, essentially nudges the network to favor smooth and low entropy functions like polynomials, sinusoids, and exponentials. If you give it a lower value, it will include nasty functions like polylogarithms and stuff like that, which we don't necessarily want. But again, this is something these things are interesting parameters to play ourselves because we don't know what type of underlying physics is. But I don't think cavity frequency has a polylogarithmic dependence on any of these parameters. So I'm using these values, setting it up and starting the training. It would take around 5 minutes, I believe. So questions while it trains. From the last set, this set, general.
So this model is the claim that it's learning the underlying physics of learning parameter mapping, or is it learning much more constrained to the individual device that you're training? Like, is there more flexibility in, like, say, the age invariance in this case?
I would say it's learning the underlying physics because the data set it's seeing is me curating this data set. Right? I have done the sweeping of the simulations. I have done the quantum analysis. It's learning what I gave it. That's the only thing that it has. If you're happy with that explanation.
Is it possible to transfer?
Yeah.
Then actually getting to a particular device by then, what we're doing is like adapting how important ours is now.
How much can I share about our proposal ideas? Or is it not allowed? So there is a lot of transfer learning ideas that I've proposed, and yes, one of them is that. But I think, as once we all contribute our data sets to us, we can build up a ginormous data sets of different Hamiltonian variables, different physics, or different geometry stuff, and we can do a lot of transfer learning so that we don't have to retrain the same physics. If it understands how cavity frequency and total length for any meander is related, it doesn't need to relearn that. That's really promising. I think it's really, really promising. Yeah. If there's any program managers on the call, give us money, please, because I'm really interested in doing this. Other questions? Yeah.
So this is going to be quick too.
Almost.
How long would this take you on an HPC in a model that we actually?
So we need to do the hyperparameter study first. So there's like a fixed setup cost. So I need to sweep over these numbers to figure out what numbers make most sense. So that will probably take hours. But once that is done, and I do pruning, which I'll say what that means, minutes, same numbers, because these things are not inherently. I guess it'd be a little faster because I can run it on a GPU. We have NVIDIA GPUs on our HPC. Still minutes, because GPUs are so much faster in handling tensor processing stuff. It's done. Okay, 2 minutes, 39 seconds. You can see it did learn stuff. The regularization is not great, but again, I intentionally gave it numbers so that I knew it would finish on time. Let's keep on looking at it. So I'm revisualizing the learn plot. All of a sudden, as you can see, it already learned that the claw length really doesn't matter as much to the cavity frequency. So that's physics that it learned on its own. So basically, this was the point I was trying to make, that it can learn the physics, but what's recommended in the paper and in practice is you have to do what is known as pruning. So it essentially redoes an optimization and makes sure that it did not, there's something known as cross attention. It makes sure that it did not miss some dependence, which does actually play a big role, but it's, it just does another heuristic search essentially. But for this data set, what happens when I do the pruning is it kind of, oh, actually, no, wow, this is stochasticity stuff, yeah.
So I have a question related to this model. This is like time to train them, and is the expectation that everybody just trains their own model, or would there be like special times? Maybe have a centralized repository where we have somebody trains a large model on an HPC, and then just like which has Java just to connect to it and just extract that.
Yeah, great question, and I had the answer over here that I didn't go over. SQuADDS is the centralized repository. At least that's what I want it to be. And within these like 3 lines of code, and I didn't really do this, TensorFlow, Google did this for us. You can literally just give it your model, your trained model. You give it whatever your repository is, and send me an email, and I'll add it to the collection. Another thing, thank you for that. Another thing I needed to shout out: Olivia Cito and Sarah Sussman from UT Austin and Fermilab, respectively. They've been doing a lot of work in model development for us. And for, again, just understanding how. Yeah. Yeah, it's on our Hugging Face stuff. Okay. Yeah, I am the resource at this moment in time, but. Yeah. Cool. Okay, where was I? Great question, though. I should have mentioned that. Okay, so yeah, yes, sorry.
The lines in the boxes, are those like plots of the function for each parameter?
Yeah, so it's things that, let's say this is negative x-ish, yeah, so negative x is the function it learned for cavity length. Then it multiplies this by this, whatever this wonky function is. And that's how it thinks that the cavity frequency is related by the multiplication of this function times this.
So this whole thing is representing
input parameters. Yeah. Yeah, and I'll show you, like you can symbolically get that from here as well. So again, it's already gone a little haywire because when I ran it last night, I still had some, after pruning, they did come up with a small dependency of this on this. So it's going to be interesting to see. Again, I should have set the seed fix when I was doing this, but it's interesting. We're in domains that I don't know what's going to happen. So that's one. So this is also recommended to, once you've pruned the model, to quickly train it again to find out if there's any added, if it missed anything in its first training. But after that, essentially what we want from the model is this. How does the cavity frequency look like as a function of the cross length and claw length? I can take questions for, actually, no, it's almost done. So, and this is where it has, in its own training, just one sec. In its own training, it has gone over different bases of functions that was set by the initial B-spline methods and those cross entropy terms. But right now, I'm forcing the model to kind of use these basis functions to give it to approximate the function that it learned on this basis. So it's gonna do that for us. But yes, a question while it does it. It's called PyCan. PyCan is the, like, you do pip install PyCan. It's on the setup instructions that I had. But in the library, it's called can. Other questions while the model is learning? Say that one more time, sorry.
Like, you want to optimize, right? Like, you have multiple different. You could have combination.
Mm-hmm. Yeah, you can. Oh, I see. You're saying, like, let's say you said, correct me if I'm wrong. I'm interpreting your answer or question as, let's say you know that the first layer has like sinusoidal or whatever. Could you intentionally have said it in that way? Is that what you're saying? Yeah, you can. But in this case, I am pretending that I don't know how cavity frequency and these terms are related at all. I want the model to do the thinking and the physics discovery for me. Yeah.
So what is the shape of that function like mean physically?
It's this.
It's sinusoidal.
Yeah.
What does it?
So that this is the function. That model corresponds to this function. So it's basically saying cavity frequency equals minus that number times total length minus a very small number times claw length minus a very small number times the sine of a smallish number times this. So I have this. Yeah.
What does that dot?
This is just the, so remember how I talked about the B-spline stuff? So this.
You said that
Oh, it's just, yeah, x against, so sorry, yeah, I understand point. Whatever this node is, which in this case is total length, against the top node, so cavity frequency, and then you, yeah. So this is the formula we get, and let's plot this against our stuff. So this is what it looks like fitted on our, to some data set that it fixed. Not a bad fit, not a great fit. But let's do some physical analysis. So this, the trained model gave us this sort of a function. Okay, it's like ax1 plus a2x2, a3 times sine b1x2 plus b2 plus a4. Order of magnitude physics. We love approximations and we love canceling out terms. Let's look back onto the magnitude of each of these numbers and see what we can disregard, which I've already done over here. So the numbers did change because I did not fix the seed, but I believe the order of magnitude still remains the same. So A1 has 1.6 e minus 3. Similar. A2, sorry, this is going to give people headaches. Just give me a headache. 5.3 minus 12. So it's also a small numbers. I guess these are the same, not the exact same digits, but the same exact order of magnitude. So if you think about the data set that we were sweeping these over, which is from these ranges, these are the total order of magnitude you get. And you can see that you can cancel out this a2x2 and this a3 sine term completely. And this is the formula that you get out from this, where this a1 term is a negative number. Yes.
So I have a question. So have you compared maybe your machine learning results with something like this, or like multivariable regression? Kind of the typical way that people used to do it.
Yeah.
You have a set of data, you have the various parameters like a factorial path
Mhm.
experiment, and you just do multivariable regression from order.
Yeah.
How is your how does this compare to that?
So I have done those. That's like the first thing I did 2 years ago now, and this thing I did over the weekend. So I need to look back on my data sets, but this is just getting the point of this is to, again, sanity checks. Let's see if the model can understand what design space parameters are of relevance, and if it can get the physics out, which the regression model get the same thing. The regression model actually is a better fit to the data because we in that case it's a human in the loop process. I knew what I wanted to fit it to, but so I think this is why it's more interesting because I did not tell it anything. So the task number 2, and I'm almost done talking, is for y'all to pick and choose your favorite Hamiltonian parameter, find out what its corresponding relevant design space parameter is, and see what result you get, and see if it makes sense physically or not. And the last task is another thing that G is an interesting case, because G is a parameter that we don't really fully understand how it depends on design parameters. I trained this model Sunday night, and I got this expression. I want you all to think about this. It fits our data actually fairly well, I would say. Does this make sense? So talk about amongst each other and see if this makes sense or not, and then I am done with the workshop, and you guys can now actually do things. Sorry, it took a long time. But that's a third task. Yeah, you guys can start playing with these things, and I will get back into those questions. So for the online folks, do you know which one I started? It was just this thing? Okay. So the idea for the online folks was essentially we wanted to create how loud should I speak for this? This is good. Okay. So sorry, folks. The idea for this was essentially there's this lasso model. It's a very common model in machine learning that we are using to essentially correlate Hamiltonian space parameters, which are these things, to the design space parameters in our data set. And we run this lasso model. This is a SQuADDS object that I wrote. And this is how you get this heat map, where each element in this heat map is a number constrained between -1 and 1. And the closer it is to like absolute magnitude of 1 means that's the importance of that particular parameter on your Hamiltonian parameter. So this is what I'm meaning, saying that, okay, it discovered that for the qubit frequency, it just basically does some correlation tasks and some minimization of error. And it just identifies the most relevant design space parameter for each given Hamiltonian space parameter. So that's it. And it's also the sign is the proportionality between these two things. Real quick, I think the online folks can hear me too. One quick announcement, folks. So I am a lead organizer of something called Summer of Quantum in LA. It's a part of, like, this year is the International Year of Quantum as designated by the UN. And we are organizing 10 different events over 10 different weeks over the summer that we are trying to get different segments of the public to come learn about quantum stuff, do fun events with us. We realize like most people get their education about quantum stuff from Hollywood, and that's not the most reliable resource. So if you all are wanting to help out with this as volunteers, please sign up. If y'all have funds or have access to people who have funds and want to sponsor us, please also connect us to that. There's a lot of fun events that we're putting up, so please, I just wanted to quickly share this with everyone before I forgot. I had one other thing to add. For one more second, folks. So there was another resource that I wanted to share that I forgot to. I did unmute, I believe. So once you go to the SQuADDS doc site, first of all, there's a bunch of tutorials. You can learn a bunch of things from there. There's good documentation on all the methods and stuff we have implemented. At the same time, I have integrated SQuADDS with Deep Wiki, where it's not quite indexed to the last release, but you can chat with the code in the sense that you can like say, hey, how do I make a qubit with frequency 4.2 gigahertz or whatever. And it should talk to the code base, figure things out, and give you the code stuff. So that's also something that's there. I have also added Qiskit Metal to this as well. It works fairly well, but that's another resource that I forgot to share initially.